Hello, Seaperch. My name is Xavier Kabansik. I'm the captain of the Angry Ducks, which is a team based out of Patriot High School. So what I'm going to be explaining to you in this video is what is CFD, why I think you should use it, and then how to use it. So CFD stands for Computational Fluid Dynamics. It is used to model the flow of water around or through an object. And it's useful for Seaperch because you could use CFD to analyze the flow of water around your ROV, which will help you reduce drag and reduce turbulence, which will increase the speed of your ROV. So it doesn't matter if your ROV is really big in PVC, if it's a mixture of PVC and 3D printed filament, or it's just 3D printed filament. It's useful in all sorts of situations. All that really matters is that there's water passing over your design.
Alright, so to start off with this tutorial, so first you're going to need to get Autodesk CFD from the student license section of their website. If you have got an Inventor with a student license, this is the same type of way. So once that is installed and updated, then you should be good to go. You may have to restart your computer for you to be able to launch CFD through Inventor. So I've already done that. There's already tutorials online. I'll have them linked in the description below. So now that you have your CAD model in CFD, in Inventor, what you want to do next is click the simulation section, which is at the very end, and click active model assessment tool. And then it'll ask if you want to save. In my case, that is no. And it will launch Autodesk CFD. Okay, I'm just going to cut this part out so it's faster. Alright, so now it has launched CFD and is going to do a model assessment to find any potential problems. This, if there are issues, you may want to consider adjusting your CAD model to make it, more simple. If like you have any crazy extrusions or things like that, so CFD will be able to understand, will be able to mesh your model. But we can mitigate a lot of these meshing problems using a technique called surface wrapping, which there will be a tutorial linked in the description below. It's a very simple process that I'm going to go into once this is finished. So while we're here, I could talk about how CFD is really a means to an end. So once the simulation has completed, like you'll see a bunch of here. I'll show you an example. So once it's completed, it's going to look like this. There's tons of interesting, things you can use to view your simulation results, like a plane, for example. And also just to disable this axis, which isn't really that useful, click axes and turn off show local coordinate axes. And yeah, this is a bisecting view the uh, um, of the model. So I mean, if you don't understand fluid dynamics and uh, hydrodynamics, I would suggest looking into that first. There are a bunch of great resources on the internet that you can view to understand this. But I will be getting into that later after this assessment has finished. Alright, so the model assessment has completed, all green checks like you'd want to see. So we're going to click surface wrap. Surface wrapping is useful. It has a higher chance of working than traditional meshing because it eliminates a bunch of small details that would normally not be friendly for simulations, like very small gaps between, like, let's see, this pipe and this L joint, and other small details that won't affect the overall results but will help reduce the computational time of the simulations. So now that this model has been imported into the surface wrapping um, area of CFD, we're going to want to click external volume. So you can you can choose a specific volume for the external volume, or dimensions for this external volume. But what the rule of thumb I go by is you want your external volume to be at least 5 times as wide as your ROV on each side, because the larger it is, the less chance that there will be an error caused because the wake of the ROV extends to the the symmetry or walls of the external volume, which would cause interference. Like think of this like let's say you have a submarine in the ocean, um, versus a submarine in like a large Olympic pool. So like when the submarine moves in the pool, the wake of the submarine is going to crash into the sides of the pool and alter the results. You need to focus on making sure that there's adequate space for the simulation to run in. So we're just going to make this fairly large, and you want this little cross to stay in the middle, so you know it's roughly equal on all sides. Yeah, you can make this as big as you want it to be. I mean, generally the bigger the better, but that will increase the simulation runtime, and you want to make sure that that your results don't take hours and hours to get, because that we're on a limited time span. So just consider that. Right. So now that we have it's not even. Let's adjust this a little bit more. Okay, perfect. So we're going to move to the side view. So again, we want to make sure. So from the front, we want to give enough space for the water flow to start in the front and pass over the ROV. So we're going to move this out about to right there. And the wake is going to be much longer. Generally, you'd want this to be like the longest. Like you want the length to be the longest um, of each of the dimensions. So bring this back a generous amount. All right, that looks good. So now we're going to click close and resolution factor. So you generally 5,000 is okay, because you won't lose that many details. But if you have a more complex design, then like specific ducts or fins or other elements, then you may want to turn this up. So I'm just gonna set this to 6,000 for right now. And after that is done, I'm going to click generate the wrap, and it's going to start wrapping the surface of the ROV. And this will take won't take too long, but be prepared to wait. All right, so the wrap has been generating. So what we're going to do is transfer this to the setup. Takes a moment, but does not take that long. So the screen may go black at sometimes, but that's okay because it'll normally fix itself once it's in the setup. Well, yeah, one thing you should know is that like 95% of the time, Autodesk CFD works really well, but that 5% of the times it may crash. So just make sure you save your data, and I'll pause and pick up when it resumes. Okay, that didn't take long. So what you're going to do now is first define our materials. So um, if because we did the surface wrapping technique, it combines all of these small parts into basically one volume, and that simplifies things for the computer, and it reduces meshing errors. So okay, so the second volume is normally water. Let's go back over this. So materials, click this, right click. So all we really care about is the name and the type. So fluid water, apply. And just to make sure we got it, that this is the water, I'm going to click outline. So I made a mistake. So that's why it's important to check these things. So this is actually a solid, and since our bot is primarily PVC, I'm going to find PVC and click that. Now this is the water. See how it's red? So water, and then I'm going to right click outline. So as you can see that, let's see, PVC shaded. Okay, so now we know that this is for sure the PVC and this is for sure water. So I'm going to make this shaded for the next step just to make it easier, which is defining the boundary conditions. So the first thing we're going to want to do is define the inlet. and that's very simple. So I'm going to click on the front, click edit, and so this is where define how fast the water is moving around the bot. So I'm going to go with 0.3 meters per second, which is 30 centimeters a second. Now, you can of course change this depending on how fast you record the speed of your bot moving in the water. So let's click apply. And for each of these, I'm going to click all of them. We're going to make these slip symmetry. Apply. And now at the back, so because we want the water to go from the inlet to across the bot, we're going to make this a pressure. Where is it? And keep that at 0. And because there's no pressure, pressure 0, apply. Okay, so we have all the surfaces defined because there's 6 sides of a cube. Okay, so then we are good. Now, if you mesh this in the normal way, you would have to right-click on mesh and click auto size. There are tutorials for that you can find pretty easily. But because of this method, we're only testing the hydrodynamics of the water around the body. Uh, so we're not going to need to do that more complicated mesh. Solve. Now this is where the magic happens. So um, we want to select steady state solver computer. So if you choose to use the cloud, you can, but I'm going to run this off of my computer. Start at 0 and then select the amount of iterations, like the maximum amount that you want. So if your thing is bigger and more complex, you're going to want a higher number. But I'm just going to put in, let's say 450. It will stop before it reaches this amount if it finishes. So that's just good to know. So for solution control, I'm going to make sure intelligent solution control is on for this. And for the result quantities, we don't want temperature, but we do want turbulence. Right, unclick these. Maybe add in absolute velocity and pressure coefficient if you want to look at those. And yeah, that should be good. So that was solution. That was result quantities. For physics, incompressible, turbulence, we're going to do SST, K omega, and turbulent. Advanced. Don't want any cavitation. No. Okay, we should be good. Okay, we're good. So I'm going to click solve. And it will get there. So, alright, so it goes black every once in a while, but it normally comes around, so don't click on it too much because it may crash. So it's important to know that there are 2 types of tests you can do. One type of this type of test is a wind tunnel test, and it shows the effect of the body on the fluid moving around it. The second type of test is a test where you isolate the propeller and the slash motor moving, so you can see how the water may flow through the propeller itself. That's a lot more complicated, and it's more of an advanced area that you could go into later if you decide you need that. So what this wind tunnel test does is it shows the object in the scenario is not moving, but the fluid in this case is. This test is the most useful for improving the hydrodynamics of the body of the design, because because just having, like, as opposed to the second test, which is just propellers, the water is stationary, so you won't really see how water moves around your design. But with this test, your bot, it's like an actual wind tunnel test when you hold your, like, imagine like you're holding like a boat in the water and the water is moving around it. Whereas the other test is the water is still, but you're holding your boat in the water and the propellers are moving. If that makes sense. So looking at the hydrodynamics of how the water flows around your design is the best way to improve your bot's efficiency and speed because it allows you to minimize the drag and reduce turbulence. And minimizing drag, reducing turbulence is very key for elevating the performance of your bot and making it more efficient. And it's much easier to improve that than by increasing the thrust, since we can't change the type of motors that we're using, and you can't really change the propellers unless you can find a viable alternative. Yeah. So that said, you can increase the efficiency of the propellers depending on how you streamline the flow of around your bot into where the propeller intakes water. Um, and that can be accomplished by understanding fluid dynamics and optimizing the flow of water so it's more streamlined and maybe even ducted into your propellers. If you're interested in the second type of test, this there are also tutorials online for that. It is more advanced, and I think it'd be a more valuable use of your time to focus on just the simple type of test because you could yield a lot of great results. So what is happening now is uh, the CAD. That's just to recap. So the CAD was taken from Inventor and into CFD. Now Inventor, to create that CAD, when you create that CAD, it makes a bunch of really big triangles to create the volume and surface of it. And these triangles are brought into CFD and divided into smaller triangles to create a good resolution mesh that can be prepared. And then after that, so that the volume mesh is after you create the surface mesh, which is creating the smaller triangles on the surface of the volume, then the volume mesh is created by dividing the whole volume into smaller cells, which are then modified based on the surface mesh to create an accurate model that can be used to simulate the flow of the design, the flow around the design. So I will resume this once the simulation is complete. It'll just be meshing for, it won't be meshing for too long, and then the simulation will start, and you'll see basically really warm colors on the front, on the inlet side, and the rest of this will be blue. But as it goes through iterations, it will progress, and eventually, like, you'll be able to see the final result. Okay, so now that the simulation has started, you can kind of see what I was saying. So at the front, you'll see that the colors are warmer than they are in the rest of the cells. That's because this is the inlet velocity. This is the inlet, so that's where water is coming in from. And as you see it as it iterates, which you can see right in the output bar, that as the iterations progress, the water will start flowing across the entire volume, and it's what it's doing there is essentially calculating how the water is traveling, and it's doing complex mathematical equations to determine exactly what's happening when the fluid goes around the body of your design. And you'll see this convergence plot where basically some of these lines will converge, and um, it will eventually converge, and that's when you'll know that the simulation is either coming close to the end or it's about to end. And I will pick this back up once we've finished the simulation and start showing you how you can analyze these results. Okay, so the simulation has finished, and let's begin doing the analysis. So let's close the output bar, and looking at this, it doesn't really look like anything, but we can, that this is just the global view. If you click plane and add plane, let's turn off the local coordinate axis. So this will show you basically a plane is going through a specific section of your ROV. You can drag this plane to see different parts of it, to see the flow moving around the object. And just to show you what it's like, so if we, right now it's clipped, and if you want to unclip it, Okay, let's do PVC shaded. There we go. So that's how you see the entire object. And in case you want to use one of the other result um, methods of analyzing the results. So let's click back on the plane. So this is just the vertical plane, of course. So we can unselect this, add a plane, and if you click edit, go to normal, make this x value 0 and the y 1, click hit OK, and boom, that's how you see the horizontal view. Now, because the top of the RV is in the way, you can get rid of that by clicking clip. And if you don't see it, that means it's on the bottom, but if you want it from the top, then you click reverse clip. And if you see these weird lines, you can just click water, and then they should go away, or the volume that is water. So yeah, so you can see a lot of the color. You can see a lot of blues and some greens. So these correlate to the speed of the water moving around the ROV. So like a lot of the water is moving. If you hover over with it with your cursor, you can see that you can see the value in the bottom on the bottom of the screen. It says this is moving at 29.9665 centimeters per second right there. Right there, it's moving at 29.89 centimeters per second. And okay, so yeah, let's move on to the next way you can look at the results. Click plane, clip. So if you want to see how flow moves over with specific traces, you may have seen this before. So in like videos. So click add, click that, click that. So that's just like a rough idea of like how it's flowing over in these specific areas, but we can modify this. So add, and then if you don't want this to be a rectangular shape, let's say a circular shape, and you want more of the traces, you can decrease the seed density. So click there, click add. And you can even animate this too and change the time of the animation. There's a lot of options to mess around with to get different results. You can even uh, make the width of them smaller so it's easier to see and change the shape. Spheres if you need that. Ribbons. It's all up to you. So that is traces. Oh, I forgot to mention. So if you go into planes and let's get back here. Let's clip this, reverse it. Okay, so this is good for telling you just like the regions in the specific plane of how fast water is moving. So you could use your understanding of fluid dynamics to, make adjustments. But if you want to see the direction of the water, you go to vectors. Then you select velocity vector if your plane is showing velocity. And now you have some vectors to see that. Now, since these are a bit spaced out, let's reduce the grid spacing and reduce the length. So now we can see how on this plane that the water is, wants to be pushed outwards because there is a slower moving region of water right here. Yeah, so like the more fine you get, the more arrows you get, so you can determine what's happening. And this works no matter where the plane is. You can just drag this. Now this may lag your computer, so don't add too many. You can see how the arrows start to move actually out of the plane because they're trying to move around this circular shape, and because of that, it's slowing down. So that's something to take note of. All right, so now let's look at Now, so planes are great for viewing it, how the flow looks in 2D, but if you want to see in 3 dimensions, you can use ISO surfaces. So this looks kind of confusing, but basically what this is showing you is where the water is moving at a specific speed. So in this case, it's 19.31 centimeters per second. And you can change this to see, okay, so where's the water moving at, let's see, above where we put the inlet speed at, so zero point 0.3, which if you remember is zero point 0.3. So as you can see, that's where a lot of really fast moving water is, which isn't necessarily a good thing because more disturbed water will tend to speed up as it goes around something, but because it's moving around something, that means that there's a region of slower moving water behind it, and I'll show you what that looks like in a moment. So yeah, you can adjust this, and let's disable this. So another good detail to add is that there's more, of course, there's more than just um, velocity. You can edit this plane to show turbulent kinetic energy. It shows you where there is turbulence. Um, turbulence is basically when the water isn't moving in a smooth um, pattern because the flow of water has been disturbed. It's generally a good idea to reduce that to increase the speed of your ROV. So yeah, there's the axes for turbulence in centimeters squared over a second squared. Okay, so let's disable this clip. Okay, so this is also really important to know. So uh, this video isn't about how to analyze simulations, more just how to run it, but here's a couple good things to take note of. Let me pull them up. So generally, we want to avoid a flow separation because that causes turbulence in the wake of the ROV. Um, and turbulence is essentially an area where the water is moving at a really slow speed and has a lower pressure than the water around it, which causes the water, let me annotate this, which causes the water to want to pool this way, which is essentially an anti-thrust, um, which would slow down your ROV. Now, of course, because your object exists, there is going to be some turbulence in some areas that have low pressure. But it's a good practice to try to reduce turbulent areas to increase the speed of your ROV and the overall efficiency. Secondly, so here's just a little view of how, like an example of how water moves around objects. So as you can see, water that contacts an object directly has an increased pressure than water moving around it because the surface it's going to is essentially flat in that little small region of this oval. And as the water moves around an object, that creates friction, which will slow down your ROV. Which is why you see some teams, I mean, some like real life vehicles, like boats, they have and surfboards, they have you can apply a special wax or coating to make your the vehicle more slippery. Here's a more detailed view of the water flow. So as you can see, there's some of the water is going to hitting a surface that is directly perpendicular to the flow of water, which causes more pressure. You'll see that there's that most of the water starts to move really fast at a higher pressure and velocity than water more towards the middle, and it continues moving like that out away from the object. And now because there's how this water is moving, that creates a flow separation, which again it creates a low pressure and turbulent wake, which you want to reduce to increase the speed of your ROV. And this is an example of how you can mitigate that by using an airfoil shape or a teardrop shape. So this reduces that turbulent area, which is more optimal for moving faster underwater. You can see that how the water has more time to attach to the body and reconvene. And you can see how this area is slightly smaller, like than this area, which has a wider or a more gradual curve. It's just some things to think about, of course. So yeah, the last thing that you may want to know is how to find the coefficient of drag. I'm going to get into that right now. And so here is how CFD might look for other types of ROVs. So as you can see, this is more of a V-shaped ROV. Zoom in. And let's see how that looks with a plane attached to it. So let's enable this plane, edit. Let's make it horizontal. And let's say you want to see how much drag is caused by this V shape. So what you would do, move this upwards, go to the top view, hit clip. Let's make this bigger. So as you can see, there's some of the things I was talking about, where as you can see the water that contacts the flow directly. Let's turn on the vectors. As you can see, so like the water that contacts like the very front directly moves a lot slower than the water moving around that region. And you can see how this water that's moving faster around the outside speeds up because a lot of the water moving directly on the outside kind of in interacts with the water moving farther away from the outside of the ROV, which causes the pressure to increase in this area and also the velocity to increase, um, which that is why you see more red right here and why you then see some blue right here too. So this is right there is an example of a turbulent wake, um, and you can see the same thing on the other side. And here's the other ROV. It's more of a miniature version of the first one we're looking at. It's more compact. So whip out our plane and click edit. Now it's horizontal. Okay. As you can see, the wake of this RV. So I'm just looking at the green area is smaller than the original RV. You can look back in the video to see what I'm talking about. So that would help it have less drag overall. Now, that doesn't mean that it's faster because the ROV has it doesn't mean that it's faster because the ROV uh, is more than just one singular plane. You have to look at it in multiple different ways to figure out what is the best design and how to make improvements. So here's another final example of uh, something you might want to consider doing to improve your art. Here's another example of fluid dynamics. So as you can see, there's a circular support right here, and directly in the front, where the water is traveling towards it, the velocity of the water decreases significantly, and then uh, the flow of the water moving around this little bubble or stagnation region has an increased velocity.
Let's turn on the vectors.
And yeah, you can see how the water right here is more disorderly or turbulent, and how the water moving around here is more laminar or smooth. So using that, you could create a more efficient ROV that will have a more optimized flow of water moving around it, which will help it move faster. And so that concludes the tutorial on how to set up and run CFD. If you have any questions, make sure you ask them in the forums, talk to your mentors and your peers, and don't be afraid to use the internet to find resources to help guide your journey along this path. I believe that each and